Hello everyone, let's solve the question number 18 of GATE paper CS1 2025. Let G be any undirected graph with a positive edge weights and T be the minimum spanning tree of G. For any two vertices U and V, let D1 of U, V and D2 of U, V be the shortest distances between U and V in graph G and MST respectively. Which one of the following options are correct for all possible G, T, Q, and V? Option A, D1 of U, V is equal to D2 of U, V. D1 of U, V less than equal to D2 of U, V. D1 of U, V greater than equal to D2 of U, V. D1 of U, V less than equal to, not equal to D2 of U, V. So, to understand this and solve this question thoroughly, we need to walk through two conceptual layers. Understanding the difference between shortest path in a graph, which is D1, and the path in a minimum spanning tree. And let's understand what is a minimum spanning tree and what it preserves and what it doesn't. So, let's understand what is a graph. So, graph is a undirected, directed, or connected like this, something like this. This is a graph. It can have cycle, it cannot have a cycle. This is somewhat we call a graph. So let's go a bit into the definitions of the same. So graph is an undirected, connected, bidirectional, or like directed. It contains positive, negative, any kind of weight it can. Uh, for now, we can assume, like, since nothing is given, for now, let's assume it has positive weights. Normally, it can have negative weights as well, and there are algorithms like Bellman, Ford, and everything to handle them. So, shortest path is defined as D1 of U, V. It is computed using Dijkstra algorithm. It is also computed using Floyd, Warshall, and Bellman. Okay. What is an MST? MST is a subset from the graph. It does not have any cycle. Okay, so it connects all the graph with minimum total edge weight. So suppose this is my graph now, for example. As you can see, there are cycles, but what an MST will somewhat look like. This is what an MST will look like. No cycles at all. It is a subset of graph where the cycles have been removed. Now, with cycle will be removed, I assume that these have the, like, this particular structure had the minimum weight. I'm assuming that. I'm not saying this can have. Basically, that particular structure with the minimum weight, basically minimum total edge weight, that is what we consider as MST. I hope the theoretical part is over. For any two vertex U, V, there is only one unique path between them. Okay, so that was a bit of theory. The distance, total distance d2 of U, V is the sum of edge weights along the unique path in an MST. Okay, so let's go a bit of differences. In graph, it can have cycle. MST does not have cycle. Graph can have many paths from source to destination. MST will have one possible path, minimum spanning tree, as the name suggests, minimum total edge weight path. Uh, in graph, we check the minimum over all the paths, but in minimum spanning tree, sum over the only available path. And yeah, I already explained it with help of an diagram about the both of one. So how do we build MST? Let's also get that. So either we build it using Kruskal's algorithm or we build it using Prim's algorithm. These are two algorithms which help us build a MST. Okay. Kruskal uses union find algorithm, union find, and the Prims uses kind of a BFS. So let's go back to the question again. So for any two vertices U, V, let D1 of U, V the shortest distance in graph G and D2 of U, V be the shortest distance in the MST T. So let's check the first option. D1 of U, V is equal to D2 of U, V. Okay. So distance 1 of U, V, it is the shortest distance in graph G, d2 of u comma v in graph T. Now, graph G can have cycles. Okay. So let's assume that this is the shortest path, like can have cycle. So let's take a graph, complex one. So maybe I can connect more. I want to find the shortest path from a particular point to particular point. So in graph, you can say that like MST के अंदर they are not equal. You cannot say that the minimum distance of a graph will be equal to the minimum distance of an MST. Why do I say that? Let's say I want to reach from here to here, and like so, I will go this way. At the same time, let's take a bit of complex graph. So if it has inner cycles, then let's say it has inner cycles. So I created a very complex graph from this to this. So to reach from here to here, there is a direct way as well. So what I'm trying to say, they are not equal in general in MST. Okay. Uh, in general, they can be equal. It's okay. Like can be, as I said, it's not compulsory. Like strictly equality, I cannot say. Strict equality, I can never say. So yeah, option A is incorrect. Let's check option B. So the option B is d1 of u comma v is less than equal to d2 of u comma v. So in the graph, we always pick the minimum cost path, MCP, let's call it. In MST basically, which is the T, we are constrained to a specific subset of edges. So what subset? The acyclic one. We don't have cycles in MST. Uh, it cannot be like optimal, may or may not. So it is possible that the graph path has less than equal to, because the graph does not have a, like, what do you call, weight constraints on it. Graph does not have a weight constraints to be found out. MST does have, because minimum total weight path it takes. So it can be less than as well. Equal to is also possible. Uh, this is one case. So option B. Let's see option C. Greater than equal to, like, no, in not equal to, you can say that they are not equal to, but in not equal to, you are actually accessing about less than, greater than, and equal to all the cases. Equal to is possible, less than is possible, greater than MST is not possible, because you are trying to take the shortest paths in both of them. So obviously it can be like it is not any random path. It is shortest path to come for comparison in both the graphs. So it cannot be greater. A common sense can say that. So the correct answer for this question is option B. That's it for this particular question. Take care. Bye bye. See you guys in the next question.